We want to focus on solids right now, and you remember the physical properties of solids. They have a fixed volume and they have a fixed shape. And that's because the particles of solids, they are in fixed positions and they're just vibrating in those positions. Well, not all solids are the same. So let's just take a look at several different. We've got molecular solids. The unit that forms those solids on the atomic molecular level can be atoms or molecules. The forces between those particles, London dispersion forces are possible, dipole forces, hydrogen bonds. You could be talking about water that's frozen in place, solids, ice. Properties, fairly soft, low to moderately high melting points, poor thermal and electrical conduction. Examples given are argon, methane, CH4, sucrose, which is a molecular solid at room temperature, dry ice, which is carbon dioxide that's frozen. And then we have things like covalent networks, atoms connected in a network of covalent bonds. The forces between the particles are covalent bonds, very hard in some cases, very high melting points, often poor thermal and electrical conduction. These are things like diamond, which is just carbon, which is connected with 4 different bonds in a 3-dimensional structure, quartz, silicon dioxide, which is sand, all covalent networks. We'll take a little closer look at that briefly. And then we're going to spend a lot of time on ionic solids. And ionic solids, if you remember, these are crystalline structures. They have an ordered array that's extended throughout the bulk of the solid mixture. It's cations and anions that are attracted to each other by that positive negative attraction. So we're going to take a pretty close look at that. Hard, brittle, melting point, poor thermal and electrical conduction. Typical examples, things like sodium chloride, calcium nitrate, calcium chloride. Any number of ionic compounds could fit into those examples. And then we have metallic solids. And metallic solids are very interesting. You have, let's say these are iron atoms. They could be chromium, nickel, and these are good thermal and electrical conductors. And you have what we call the sea of electron model. These are delocalized electrons that can move from one atom to another, which makes them great for creating very strong bonds between the atoms. And also, you can bend metals typically, you can beat them into different shapes. So all metallic elements would exhibit this metallic bonding: copper, iron, aluminum, platinum, nickel, cobalt, all these metals. And we call this the sea of electron model. And we talked a little bit about this in Chem 1. So covalent networks, here are 2 examples. We have diamond, which is carbon. It's what we call an allotrope. And these are 2 different allotropes of carbon. Okay? And an allotrope, just a different form of the same substance. This is representing diamond. This is representing graphite. Diamond is the hardest naturally occurring substance on the earth. You can use it as drill bits in industrial drills. It makes great jewelry. Graphite, on the other hand, is also carbon, but it's a planar molecule. Diamond is 3D, and graphite is sp2 hybridized, whereas diamond is sp3 hybridized. It's tetrahedral. This is planar. And when you, let's say, write with your pencil, okay, so if this is your pencil, what you're doing as your pencil moves across the page is you're simply sloughing off these layers of graphite. And that is what's making the image from your pencil. All right, so those are types of covalent network solids. What we're going to focus on are crystalline solids, and specifically unit cells. Okay, here are a few unit cells to be familiar with. Now, if you study solids and unit cells, you'll find that there are many unit cells, many that are much more complicated than what you're going to see here. But this will be enough for this course. It'll get you started. So here's what we've got. Reds, all the red spheres, we're going to call those A, and all the yellow spheres, we're going to call those B. And here's how you want to look at that. A unit cell is one unit, and what you have to imagine is that there is another cube of equal size that's sitting up here. So there's another unit cell that's over here, and it just keeps going. And so we have that, and then that connects there, so you have unit cell there, you have one down here, and so the bottom line is that each one of these spheres that's on a corner contributes 1/8 of its volume to a single unit cell. You really just have 1/8 of that sphere being contributed to a single unit cell. But that unit cell is repeated over and over and over in a crystal structure. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 1/8 times 8, and that is equal to 1. So this would just be A. Now, this is called a body. This, by the way, this is a primitive cubic. It's also known as a simple cubic. So those represent the same type of unit cell. Here we have a body-centered cubic, and in a body-centered cubic, you have an atom or ion that's dead set in the middle of the structure. And so easily, that contributes all of itself to a single unit cell. Again, we have the 8 1/8 of the reds on the corner. So that gives us 8 times 1/8 reds, which is just the 8's cancel, and we get a 1. So that's an A. And then we have the 1 yellow, that's a B. So that's just 1, and that's your B. And so our formula, our empirical formula for this substance is AB. Let's take a look at a face-centered cubic. This face-centered cubic has the corners. We're familiar with those now. Those are the reds, and that's the 8/8. So the reds will be 8 times 1/8, which again is just 1 red. That's the A. And then we have these guys. And each of the yellows in this face-centered are contributing 1/2 of their volume to the single unit cell. And we have 1, 2, 3, 4, 5, 6 of them. Okay, so 6 of those. And so that's 1/2 times 6, which is equal to 3. So we've got 3 B's and we've got 1 A. So our empirical formula for this unit cell is AB3. That would describe the empirical formula for that particular unit cell, AB3. All right, let's move on. And you can see this is a description, much neater description of what I just did for all 3 of these unit cells, simple or primitive, body-centered, and face-centered cubic. Let's take a look at an edge-centered cubic. All right. So each one of these atoms or ions, and these can be atoms or ions for a unit cell for a crystalline solid, and each one of them is contributing 1/4 of its volume to the single unit cell. What you have to imagine, guys, is that there's another unit cell up here, okay? There's another unit cell out here in this corner, okay? So there's another unit cell here. Oh boy, my artwork leaves a great deal to be desired. There's another unit cell down here, and they're all of equal volume. I'm just not going to try and clean up this artwork. But each one of these atoms or ions contributes 1/4 of its volume to the single unit cell. And we call this an edge-centered unit cell. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those. So that's 1/4 of 12. And so 1/4 of 12 is 3. And these are not red or yellow, but let's just say this is A3, and we'll call it an A3. Okay, so that is the formula for this particular unit cell in this situation. Okay, so here is a real formula, a real empirical unit cell. It has calcium, titanium, and oxygen in it, so it's a real ionic compound. And we're going to take the unit cell and we're going to come up with an empirical formula. This is perovskite. We're going to come up with a real empirical formula for this stuff. So let's label things. First of all, we have titanium on the corners. So the titanium is in the simple or primitive cubic configuration, and all the silver guys are titanium. The calcium is this gold guy in the center. So here's calcium. It's in the body-centered configuration. And then on the edge-centered, we have, these are oxygens on the edge-centered. So let's just deduce this. So first of all, the easy one is calcium. It's in the body-centered configuration. So there's one calcium in a single unit cell. And then let's take a look at the titanium. For the titanium, what you have in the corners, so that's 1/8, and there are 8 of them, so that's going to be 8 times 1/8. Those cancel, and so that gives us 1 titanium. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of the edge-centered. That's oxygen, which is really not that big of a surprise. And each one of these is contributing 1/4. So you have 1/4 times 12, which is equal to 3 oxygens. So our formula would be calcium, titanium, and you've got 3 oxygens here. So this would be our empirical formula for this compound. Okay, and that is pretty much all you need to know about unit cells. There's a link here in the PowerPoint notes if you want to take a look at perovskite. Okay, and I think that should do.